The vastness of the cosmos hides enigmas so profound that even our most powerful telescopes seem to tremble when pointed in their direction, as if the universe itself hesitates to reveal what lurks beyond the familiar scaffolding of galaxies and shimmering clusters. Among these enigmas, one stands apart not because of what it contains, but because of what it does not. It is a region so large, so empty, so anomalous in its very nature that it appears less like a part of our universe and more like a wound carved into the fabric of reality. Cosmologists call it the largest known void, an expanse of near-perfect nothingness stretching across hundreds of millions of light years, a gulf where the universe seems to have simply refused to place anything at all. To gaze into this darkness is to confront a silence older than galaxies and deeper than the cosmic ocean itself. It is a silence that seems to whisper a question: what happened here, and why? When astronomers first stumbled upon this unsettling emptiness, the discovery shattered the quiet assumptions that had shaped cosmology for decades. The universe was expected to be uniform on grand scales, smoothed out by gravity's patient hand and by the lingering imprint of the primordial fluctuations that seeded all structure. But this immense hollow defied that expectation. Instead of the intricate cosmic web, filaments of galaxies stretching like luminous highways, there was absence. Not a gentle thinning of stars, nor a sparse scattering of faint galaxies, but a yawning chasm where entire superclusters should have been. It resembled less a deviation and more a deliberate omission, as though some ancient force had swept this region clean, long before the first galaxies had a chance to ignite. The scale alone made it extraordinary, but scale was only the beginning of its mystery. The deeper astronomers looked, the more troubling the emptiness became. Such a void should not exist if the standard cosmological model tells the full story. The early universe, governed by uniform laws and seeded with tiny density variations imprinted by cosmic inflation, should have evolved smoothly from hotspots and cold spots into the cosmic architecture we observe today. This architecture allows for voids, of course. Every cosmic web requires negative space, but nothing on the scale of this gargantuan anomaly. Here is a region so vast that light itself requires nearly 1 billion years to traverse it, a kingdom of darkness uninterrupted by the bright cities of galaxies. If the Milky Way were shrunk to a grain of sand, this void would still be the size of a cathedral. And yet it is not merely empty, but excessively empty, a deviation so extreme that probability bends beneath it. Simulations that model billions of years of cosmic evolution cannot reproduce anything remotely similar through natural fluctuations alone. No matter how the parameters are tuned, something seems missing, not just matter, but explanation. As researchers turned their instruments toward the abyss, they anticipated distance, faintness, subtle hints of galaxies hiding behind dust, or dim clusters obscured by cosmic glare. Instead, they found next to nothing. A few meager galaxies drift within the void, like lost ships stranded in an impossible sea, their isolation unnatural, their formation seemingly at odds with everything known about how galaxies grow. These lonely survivors lack the abundant neighbors that typically shape a galaxy's evolution through tidal interactions and mergers. Their chemical signatures speak of stagnation, their stars aged and sparse, as if cut off from the universe's creative forces. They are relics of a cosmic history written in isolation, trapped in a domain where the universe's rules seem to thin alongside the matter itself. Why they exist at all remains a riddle. They are like fossils, embedded in a desert, whose sands should never have allowed life to begin. Yet the galaxies are not the only strange inhabitants of this void. When astronomers mapped the few that remained, they noticed an eerie pattern. These galaxies were not scattered randomly as one might expect in such desolation, but arranged along a tenuous line, an echo of a filament that should not have survived here. It was as though a ghost of the cosmic web still clung to existence within the emptiness, a faint scar left from a time before the void swallowed nearly everything around it. Their positions suggested that some ancient structure once threaded through this region, guiding matter into a fragile chain before some immense event or process drained the surrounding volume of nearly all substance. This alignment deepened the mystery, turning the void from a simple absence into a puzzle of cosmic archaeology. What colossal mechanism could shape a region so large, while leaving behind only a faint scaffold of what once was? The gravitational behavior near the edges of the void only amplified the enigma. instead of behaving like a typical underdense region, which would gently attract nearby matter inward as gravity attempts to smooth out irregularities, the void appears to exert something akin to repulsion. Galaxies surrounding it accelerate away faster than cosmic expansion alone should dictate, as if the emptiness possesses a strange negative pressure that pushes matter outward. This behavior challenges long-held assumptions about how gravity operates on vast scales. Dark energy, the mysterious force driving the acceleration of the universe, is known to act uniformly, but here it seems magnified, almost concentrated, as though the void is a reservoir where dark energy asserts dominion with unusual strength. This localized acceleration hints at physics that might not yet fit within the elegant equations of general relativity. It invites unsettling possibilities, variable dark energy, exotic fields, or even regions where space-time itself transitions into a different state. One of the most alarming clues emerges from the faint whispers of ancient light. The cosmic microwave background, the afterglow of the Big Bang, carries imprints of the void in the form of a temperature anomaly. Photons traveling through this region lose energy more than they should, cooling slightly, creating a cold patch on the sky that should not be so large or so coherent. This cold signature suggests that the void has been influencing cosmic expansion since the universe was in its infancy. Such influence implies a primordial origin, one that stretches back to the earliest fractions of a second, when quantum fluctuations were stretched to cosmic scales by inflation. Could this void be a fossil from a moment when space underwent transitions and fractures more volatile than anything we observe today? If so, it stands as a relic older than galaxies, older than stars, perhaps older than the very laws that govern the cosmos as we know them. The magnitude of the anomaly tempts some theorists toward more daring interpretations. Perhaps the void marks a boundary between domains with slightly different physical properties, a seam in the cosmic fabric where inflation ended unevenly, leaving behind a patch of space forever estranged from the rest of the universe. Such boundaries are whispered about in theories of a multiverse, where different regions of space-time may settle into different vacuum states, each with its own constants and laws. If the void is such a frontier, then its emptiness may reflect not failure, but incompatibility, a region where matter simply cannot persist because the underlying physics does not welcome it. This idea, though speculative, gains power from the void's sheer improbability. When nature presents a riddle that defies all conventional mechanisms, the mind inevitably wanders toward the extraordinary. Yet extraordinary explanations are not granted lightly. The scientific pursuit demands patience, evidence, and the disciplined refusal to assume what cannot be demonstrated. Still, the void resists conventional explanation with a stubbornness that feels almost intentional. It refuses to be catalogued as a mere statistical outlier or a quirk of observational bias. Its presence warps the flow of galaxies, bends ancient light, and challenges the coherence of cosmological models that otherwise describe the universe with elegant precision. It stands as a monumental contradiction, a vast desert carved into a cosmos that should not permit deserts of this magnitude, and because it contradicts, it compels. The human mind is drawn not to what is understood, but to what is missing, and the greatest void in the universe is nothing if not an invitation to question, to imagine, to search. To contemplate this void is to confront the possibility that the universe is not uniform, not predictable, not entirely governed by the equations we cherish. It suggests that reality may harbor hidden architectures, invisible currents, or primordial scars left over from an era when the universe was young, chaotic, and stranger than our models allow. It challenges us to consider that the cosmos might be far more complex, far more unruly, and far more mysterious than the graceful patterns we have mapped across the night sky. And it reminds us, perhaps more powerfully than any cluster or quasar or galaxy ever could, that the universe is not defined solely by what exists, but also by what does not. The darkness that stretches across the largest void in the universe is not merely an absence of galaxies. It is the presence of a profound cosmic contradiction, a disruption so immense that it seems to echo across billions of years. To look into this abyss is to sense a strange kind of pressure, a silent gravity of mystery that pulls the mind toward questions as vast and unbounded as the void itself. It is not simply empty space. The The universe is full of empty space, after all. Instead, this is emptiness with intent, a hollowness sculpted on scales that defy natural explanation. It stands as a monument to forces we do not yet understand, forces that appear to have acted with astonishing precision and extraordinary power. If the universe is a grand tapestry woven from matter, energy, and time, then this void is a tear in the fabric, a seam pulled apart before the threads of creation had fully settled. The enigma deepens when one considers the behavior of matter around this colossal gulf. Instead of flowing inward as gravity should dictate, matter appears to retreat, fleeing from the void as if repelled by an unseen force. Galaxies at the surrounding edges accelerate away faster than cosmic expansion can justify, as though the void exerts a kind of anti-gravitational influence. This unusual motion is subtle, yet undeniable, and it hints at a localized deviation from the universe's expected smoothness. The very idea challenges the assumption that dark energy is constant throughout the cosmos. If dark energy behaves differently within this void, if it is stronger, more active, more dominant, then this region could serve as an experimental chamber carved by nature itself, a place where the mechanisms behind cosmic acceleration reveal themselves without the interference of dense galaxy clusters or tangled filaments. The few galaxies that cling to existence within this vast desert only amplify the strangeness. They are sparse, faint, chemically simple, and starved of the raw materials needed for growth. Their ancient stars tell stories of stagnation, of formation without nourishment, of existence without connection. They drift in solitude far greater than any galaxy should endure. In regions of normal density, galaxies interact constantly. They exchange gas, trigger waves of star formation through tidal encounters, and occasionally collide to produce energetic bursts of new stars. But here, such interactions are not merely rare, they are nearly impossible. A galaxy in this void is a cosmic castaway, denied the influences that shape galactic life elsewhere in the universe. Its evolution is stunted, its potential suppressed, as though it were a biological organism raised in total isolation, deprived of stimuli and companionship. The void has shaped these galaxies in ways that stand apart from every conventional model of cosmic evolution. One of the most haunting aspects of this void is the alignment of those few surviving galaxies. Their positions hint at the remnants of a filament, a delicate thread of matter that once stretched across the region like an umbilical cord connecting young cosmic structures. But this filament appears almost spectral now, a ghost of the cosmic web, stripped of its mass, its density thinned to the brink of dissolution. Filaments do not simply vanish. They are born from dark matter scaffolding and persist for billions of years, guiding the flow of matter as the universe expands. That this thread-like structure persists here, frail and half-erased, implies a cataclysmic event or a long-term process that systematically drained the region of its matter, leaving behind only the faintest trace. It is as though the void has consumed everything it could reach, yet was unable to extinguish the last embers of galactic formation entirely. The void's gravitational imprint on the cosmic microwave background has also drawn immense attention from theorists. When ancient photons traverse a region of evolving gravitational potential, they gain or lose energy, a phenomenon known as the integrated Sachs-Wolf effect. The void creates such a distinctive signature that it has become synonymous with one of the largest cold spots ever detected. The coldness is slight in absolute terms, perhaps only a few millionths of a degree, but cosmically it is enormous. It suggests that the void has been influencing the flow of energy across the universe for billions of years. That a region so empty could leave such a pronounced fingerprint on the oldest light in the cosmos forces cosmologists to consider whether this void formed earlier than expected, perhaps even during the epoch when the first quantum fluctuations were magnified into cosmic structures by inflation. If that is true, then this void is not merely a feature of late-time cosmic evolution, but a relic from the dawn of time, an artifact from an era when the laws of physics may have operated differently. Such a possibility opens the door to even more speculative and provocative ideas. Some theories suggest that inflation could have left behind patches of space-time that expanded faster or slower than their surroundings, creating regions with different densities or different vacuum properties. If the largest void is such a remnant, a bubble of space-time where inflation behaved anomalously, it may reflect a primordial instability or a boundary between regions of different cosmic phases. In such a scenario, matter would have had difficulty accumulating from the very beginning, leaving the void perpetually underdense. The faint filament of galaxies might mark a narrow region where the inflaton field, responsible for driving inflation, transitioned unevenly, allowing just enough dark matter to collect for a few galaxies to form. It would be a fossil of creation itself, a scar left by cosmic processes so ancient and so energetic that they remain hidden behind layers of physical laws and mathematical abstractions. The idea that this void could represent a boundary of sorts is both captivating and unsettling. Boundaries in physics often conceal radical shifts in behavior. Event horizons encircle black holes, protecting the singularities within. Phase transitions in the early universe may have created pockets with different properties. And in some speculative models, the cosmos may be dotted with bubbles of spacetime where fundamental constants differ ever so slightly. If the largest void marks such a domain boundary, if it is a region where spacetime does not conform exactly to the same physical parameters as its surroundings, then the void might be an interface between different cosmic realities. Such an interface would repel matter not out of hostility, but because the laws inside it and outside it are incompatible. In such a region, particles might behave differently, gravity might weaken or fluctuate, and structures that form everywhere else might fail to coalesce. This would transform the void from an absence into a revelation, a place where the universe hints at diversity within its very foundations. Of course, the void does not need exotic physics to be extraordinary. Even under conventional models, its scale defies explanation. Simulations of cosmic structure formation begin with tiny density variations, close to uniform, and evolve them over billions of years. While these variations can grow into great clusters and vast voids, the statistical distribution of such structures is well understood. A void as large and empty as this one falls outside most predictions, suggesting that chance alone is insufficient to account for it. To reconcile the void with the standard model, one would need either extremely improbable initial conditions or some mechanism that amplifies underdensity beyond current expectations. Such a mechanism is conspicuously absent from current models, which treat voids as passive regions rather than dynamic systems with their own evolution. Yet the void appears dynamic. It expands faster than the universe as a whole, its boundaries sharpen with time, and its interior seems to repel matter rather than merely lack it. This dynamism cries out for explanation. The void's rapid expansion is perhaps its most troubling trait. While the universe's global expansion is driven by dark energy, the void appears to amplify this effect locally. This amplification could arise if the void contains less dark matter than expected, reducing gravitational pull and allowing dark energy to dominate more strongly. But some measurements suggest that the void is almost devoid of dark matter entirely, a result far more extreme than cosmologists once thought possible. Without dark matter's gravitational scaffolding, galaxies cannot form, filaments cannot persist, and the cosmic web fractures. The void becomes a gravitational desert where expansion accelerates unimpeded. If dark matter is truly absent here, the void could serve as a testbed for alternative theories of gravity, some of which predict weaker gravitational forces in low-density environments. This environment might even reveal whether dark matter interacts with itself or with spacetime in ways we have not yet uncovered. Despite all these mysteries, the void is not merely a threat to existing theories, it is an opportunity. In the absence of matter, subtle effects become visible. The structure of spacetime itself can be probed without interference from gravitational noise. Light traveling through the void can reveal tiny distortions, shear patterns, or energy shifts that test the limits of general relativity. Galaxies skirting its edges behave like tracer particles in a fluid, mapping the gravitational currents that shape cosmic flow. Even the void's emptiness is a kind of presence, an active stage where dark energy performs without competition, where the universe's expansion can be studied in its purest form. It is not an accident that some of the most ambitious space telescopes are being directed towards this region. Scientists hope that within this darkness lies clarity, that in the heart of nothingness we may finally glimpse the structure of everything. The largest void is a contradiction made manifest, a riddle etched into the universe with strokes too vast for ordinary comprehension. Its existence stretches the imagination and challenges the intellect, inviting speculation while demanding rigor. It stands as a testament to the cosmos's capacity for surprise, a reminder that the universe is not merely a place of stars and galaxies, but also of profound silences and impossible absences. And within those absences lie the deepest truths. For sometimes, in the vast and ancient darkness, the universe reveals its secrets not through what it shows, but through what it withholds. There are regions of the cosmos where silence is not merely the absence of sound, but the presence of an ancient stillness, a quiet so absolute that it seems to predate the stars themselves. The largest known void is one such region, an immense expanse where the universe appears to have retreated, leaving behind only the faintest traces of structure. To explore this space is to witness the cosmos stripped of its luminous complexity, revealing its skeletal framework and exposing cracks that run deep into the foundations of cosmology. The void stands not as an accident, but as a reminder that the universe is not obliged to conform to our expectations. It is a vast cosmic refusal, a place where the rules that shape billions of galaxies seem to falter. And as telescopes refine their vision and simulations grow in sophistication, the void only seems to deepen in mystery. The behavior of matter in the region surrounding this immense emptiness reveals a story of tension between gravity and dark energy, between structure and dissolution. Matter flows around the void like rivers diverted by a colossal obstacle, forming arcs and streams that curve around its vast perimeter. Galaxy clusters appear distorted, stretched by unusual gravitational gradients, as if the void exerts a subtle pull of its own, not through attraction, but through absence. In astrophysics, gravitational dynamics can be mapped like the flow of fluids, and the void behaves like a sink where density gradients invert. Instead of rushing inward toward a minimal density region, matter pulls away, creating eddies and channels that guide entire superclusters. This behavior is not merely uncommon, it is profoundly counterintuitive. It forces cosmologists to consider that the void might not simply be less dense than expected, but fundamentally different in its interaction with space-time. Observations reveal that galaxies near the void's edge move with velocities that exceed predictions from cosmic expansion alone. Their peculiar motions betray an underlying force pushing them outward, a force that seems to grow stronger the closer they are to the void's center. If gravity is the curvature of space-time caused by mass, then what is the curvature caused by the absence of mass on this scale? General relativity predicts that underdense regions create a shallower gravitational potential, but the magnitude of this void's influence far surpasses the expected effect. It is as though space-time itself is expanding slightly faster within this region, stretching more eagerly toward nothingness. Whether this represents an amplification of dark energy, a modification of gravity, or a relic of primordial conditions remains unknown, but the evidence is clear. The void is not passive. It influences its surroundings with a quiet but undeniable power, reshaping the cosmic landscape around it. This gravitational anomaly becomes even more striking when considering the void's temperature characteristics. Ancient radiation from the early universe, the cosmic microwave background, passes through this region and emerges slightly cooler than expected. This cooling effect should be faint, a mere whisper in the cosmic static, yet the signal is stronger and broader than models predict. Some suggest that the void's gravitational potential has evolved in a non-standard way, draining energy from passing photons more efficiently. Others propose that the void may contain exotic forms of energy or matter that interact weakly with light, but strongly with space-time curvature. Whatever the cause, the cold imprint left on the cosmic microwave background serves as a timestamp, marking the void as a feature not only of the modern universe, but of the ancient cosmos as well. It is a fossil from an era when the universe's structure was first taking shape, and its signature persists across billions of years, unchanged and haunting. If the void's gravitational and thermal peculiarities are unsettling, the behavior of dark matter, or its apparent absence, adds another layer of enigma. Dark matter is the unseen scaffolding upon which galaxies and clusters form. It defines the cosmic web, pulling matter into filaments and nodes. Yet within the void, dark matter seems nearly absent, stripped away as thoroughly as visible matter. This scarcity contradicts the understanding that dark matter should be far more resilient than baryonic matter, unaffected by electromagnetic forces and reluctant to move once distributed. Some astrophysicists propose that the void might not simply lack dark matter, but might actively repel it. If dark matter possesses even the weakest self-interactions, or interacts with exotic fields that become dominant in low-density environments, it could explain the evacuation. Others consider whether the region experienced early heating or energetic events capable of dispersing dark matter long before galaxies formed. But these ideas challenge deeply seated assumptions about the nature of dark matter, requiring theorists to stretch beyond the boundaries of conventional astrophysics. The few galaxies that do exist within this vast emptiness are silent witnesses to a cosmic story whose earliest chapters remain unknown. Their isolation speaks of a past where star formation dwindled prematurely, cut off from the intergalactic reservoirs that fuel growth. Without the gravitational companionship of neighboring galaxies, they evolved in solitude, their rotational dynamics warped, and their star clusters faint. Their chemical compositions reveal an absence of the heavy elements that accumulate through generations of stellar death and rebirth, a sign that these galaxies have remained unchanged for eons, untouched by mergers or accretion. Their presence is both a clue and a contradiction. They should not exist in a place where dark matter is nearly absent, yet here they drift. They may represent remnants of a filament that once crossed the void, stranded as the surrounding space expanded and emptied. Their faint glow is a reminder that even in the universe's darkest reaches, matter clings to existence with a kind of quiet defiance. The void also influences cosmic flows across distances far beyond its immediate boundary. Superclusters that lie hundreds of millions of light years away display peculiar motions aligned with the gravitational footprint of the void. These motions are subtle but coherent, suggesting that the void is not an isolated anomaly, but a major node in the universe's expansion pattern. It reshapes the trajectories of galaxy groups, alters the direction of intergalactic gas, and contributes to the formation of large-scale anisotropies in cosmic structure. In hydrodynamic terms, it behaves like a pressure gradient in spacetime, pushing matter toward regions of higher density. This feedback mechanism may help explain why dense walls of galaxies form around the void, clustering more tightly than elsewhere in the universe. These walls resemble cosmic shorelines, gathering matter as though fleeing from an invisible tide. Their structure defies randomness, suggesting an evolutionary history dominated by the void's growth and the pressure it exerts on its surroundings. Some cosmologists argue that the void may have formed through a merger process, where smaller underdense regions combined over billions of years. This idea gains support from the substructure revealed in deep surveys, which detect faint gradients in density across the void's interior. If the void is indeed a composite of several smaller voids that overlapped and merged, it could help explain the elongated shape, the leftover filament remnants, and the observed gradients in galaxy ages and metallicities. This merger scenario fits naturally within large-scale structure simulations, but still struggles to account for the region's extreme underdensity and its powerful gravitational influence. The idea of multiple voids merging also raises questions about why such a process would occur here and not elsewhere at the same scale. Cosmic evolution should be uniform in its randomness, yet this region stands out as a statistical anomaly. It is a puzzle with too many edges and not enough pieces. Other hypotheses explore more exotic origins. Some theorists propose that the void might be a lasting imprint of a cosmic phase transition, where a region of space-time became trapped in a different vacuum state during the early moments of the universe. In this view, the void is not empty by accident, but empty by design, the consequence of quantum fields settling unevenly during inflation. Such a region would repel matter naturally, as its vacuum energy would differ slightly from its surroundings, creating a gradient that pushes matter away. If so, the void could represent the boundary between two domains of spacetime that formed during inflation, each with subtly different properties. This idea blurs the line between cosmology and particle physics, suggesting that the void may hold clues to forces and fields that have no observable signature elsewhere. It transforms the void into a laboratory for probing the early universe, a place where the ghosts of primordial physics still linger in the geometry of spacetime. Others venture even further, contemplating whether the void might be a scar left by a now vanished primordial black hole of unimaginable size. If such a black hole evaporated through Hawking radiation in the earliest epochs, it could have carved a region of extreme underdensity that persisted long after the black hole itself disappeared. While this idea remains speculative, it reflects the desperation of theorists confronting an anomaly that resists all conventional mechanisms. Every explanation proposed must account not only for the void's size and emptiness, but also for the delicate structures that remain within it, the faint filament, the lonely galaxies, the unusual gravitational behavior, and the persistent cold imprint on the cosmic microwave background. No single theory yet succeeds in capturing all facets of this cosmic paradox. Perhaps the greatest challenge the void poses is philosophical. It forces a re-evaluation of what it means for the universe to be uniform. It calls into question assumptions about the nature of dark matter, dark energy, and gravity itself. It taunts cosmologists with the possibility that the universe contains structures shaped not by randomness, but by deep physical principles we have yet to uncover. It reminds us that our models, elegant as they are, may still be drafts awaiting revision. The void is a cosmic admonition, a reminder that the universe is under no obligation to be simple. Across the immense reaches of the observable universe, where filaments of galaxies thread through darkness like strands of cosmic silk, there exists a colossal emptiness, whose very existence challenges everything we believe about matter, gravity, and the unfolding architecture of reality. This vast void is not merely a gap between galactic walls, it is a region so expansive, so profoundly lacking in structure, that it appears almost surgical in its emptiness, as though carved deliberately from the universe's intricate design. To study this place is to stare into the universe's most unsettling contradiction. How can a cosmos that began with nearly uniform initial conditions produce a hollow of such magnitude? How can the cosmic web, the great interconnected network of matter that shapes the distribution of galaxies, suffer a fracture so extensive that no known physical process can repair it? Every new observation seems to illuminate the void's edges, only to deepen the darkness at its heart. One of the most striking consequences of this enormous emptiness is the way it warps the flow of matter on scales so vast that human intuition struggles to grasp them. Galaxies do not drift randomly across the cosmic expanse. They move in response to invisible forces created by the distribution of dark matter and the overall geometry of space-time. In regions rich with mass, gravitational wells pull galaxies inward, but near the void, the opposite happens. Matter slides away, like water flowing around a submerged boulder. It is as though the void exerts a gravitational push, not through the presence of repulsive mass, but through the absence of pull. This reversal confounds simple interpretation. Under classical gravity, emptiness should not have such dramatic influence, and yet galaxies accelerate outward, their velocities betraying an invisible hand that shapes their trajectories and guides their evolution. The magnitude of these peculiar motions has led to speculation that the void may contain clues to a deeper understanding of dark energy. Dark energy permeates the cosmos, driving its accelerating expansion. But in most regions, its influence is partially masked by mass concentrations and gravitational structures. Within the void, however, dark energy may operate with minimal resistance. Its effect could be magnified in such a way that the void becomes a glimpse into the universe's distant future, a preview of what the cosmos will resemble when matter has thinned across inconceivable distances and only the accelerating expansion remains. If dark energy varies with density, as some theories propose, then the void could be a natural amplifier of its effects, a place where space-time stretches more aggressively and galaxies are pushed apart with a force greater than the cosmic average. If this interpretation is correct, the void represents more than an anomaly. It is a laboratory for understanding the fate of the universe itself. The nature of dark matter within this region raises further questions. Dark matter, the invisible scaffolding that shapes cosmic structure, is expected to be distributed broadly and uniformly on large scales. It forms the gravitational skeleton of the universe, guiding the formation of galaxies and clusters. And yet, within the void, dark matter appears almost entirely absent. This absence is more dramatic than the mere lack of visible galaxies. Without dark matter, the formation of galaxies should be impossible. But faint galaxies do exist here. drifting through the emptiness like survivors of a long-lost civilization. Their presence suggests that dark matter once existed in the region, but somehow dissipated or was forced outward. Such a depletion would require forces far beyond the scope of conventional cosmology. Perhaps dark matter self-interacted in ways not yet understood, producing pressure-like effects that evacuated the region. Or perhaps exotic physics played a role, fields or particles that behave differently in low-density environments, escaping or decaying in ways that standard dark matter models cannot account for. The void also influences cosmic microwave background photons in a manner that suggests a dynamic history of gravitational evolution. As ancient photons pass through the void, they lose energy due to the evolving gravitational potential, creating a measurable cold imprint. This imprint, larger and more coherent than predicted, implies that the void's gravitational characteristics are not static, but evolving in ways not captured by simple models. The photons that cross this enormous gulf carry with them a record of its development across cosmic time. They whisper hints that the void did not form gradually, like other underdense regions, but may have originated from a primordial fluctuation, amplified by conditions present during or immediately after inflation. This interpretation connects the void to the earliest moments of the universe, a period when quantum fields dominated and space-time underwent violent transformations. If this void is indeed a relic from the inflationary epoch, then its existence provides a rare opportunity to test inflationary models in the present universe. Inflation was a period of exponential expansion that smoothed and stretched fluctuations, creating the seeds of structure. But inflation may not have been perfectly uniform. Some regions could have been pushed into slightly different states, settling into vacuum configurations that differ subtly from their surroundings. These differences would produce patches of space-time where matter behaves unusually, where structure fails to form, and where expansion proceeds at a modified rate. The void may be such a region, a fossil of inflation, preserved in the present-day cosmic landscape. Its anomalous size and shape, its gravitational imprint, and its influence on cosmic flows all hint at an origin deeper and stranger than ordinary structure formation can explain. The few galaxies that populate this immense emptiness paint a poignant picture of cosmic isolation. They are relics of filamentary structures that once fed them with gas and dark matter, but those filaments have been stretched thin or erased entirely. The galaxies appear to have formed early, before the void reached its extreme underdensity. Their current properties reflect an environment nearly devoid of interactions. Without nearby neighbors, these galaxies evolve at a glacial pace. They lack strong tidal forces, mergers, or ram pressure effects that drive star formation in more typical environments. Their star populations are old, their gas supplies scant, and their metal content low. They resemble cosmic hermits aging in slow motion, their evolutionary clocks ticking differently than galaxies in denser regions. These galaxies are not simply underdeveloped, they are shaped by an environment fundamentally hostile to growth. The distribution of these galaxies suggests the void may have once contained a filament or a cluster that became stretched or eroded as the void expanded. In this interpretation, the void was not always as empty as it is today. Over billions of years, gravitational forces could have pushed matter outward, gradually intensifying the region's hollowness. But this raises the question, what could drive such an extreme evacuation? Ordinary cosmic expansion cannot produce such dramatic effects. Instead, a more powerful mechanism must have acted upon this region, reshaping its structure and enhancing its emptiness. Whether that mechanism was a mixture of dark energy variability, early universe quantum effects, or unusual dark matter behavior remains an open question. The void's influence extends far beyond its borders. Galaxy clusters hundreds of millions of light years away show motions that align with the void's gravitational field. These motions are subtle but consistent, suggesting that the void plays a significant role in shaping the flow of matter on intercluster scales. The gravitational environment around the void forms channels along which matter flows toward denser regions, bypassing the void like rivers avoiding a barren desert. This cosmic redirection contributes to the formation of superclusters and walls, amplifying the contrast between dense and empty regions. The void acts as a kind of cosmic pump, draining material from its interior and depositing it in the surrounding structures. reinforcing large-scale anisotropies across the universe. Some researchers propose that the void might be part of a larger network of supervoids, structures even larger and more complex than we currently understand. These massive voids could interact, merge, and reshape the cosmic topology in a manner similar to how bubbles merge on the surface of boiling water. If the void is indeed a composite of several smaller voids merging over time, this merging process could produce some of the unusual gravitational effects observed. Yet this model still fails to account for the void's extraordinary underdensity, suggesting that merging alone is insufficient to explain the anomaly. Instead, the void may result from a combination of processes: an amplification of primordial fluctuations, evacuation through cosmic flows, and possibly interactions with exotic energy fields. The philosophical implications of this void are profound. If the void represents a boundary between regions of space-time with differing properties, then it is a doorway into a deeper understanding of reality. If it reveals unknown behaviors of dark matter or dark energy, then it is a clue to the universe's hidden architecture. If it is a relic from the inflationary epoch, then it is a window into the universe's most ancient chapter. And if it defies all explanations, it may be a sign that our understanding of cosmology is incomplete in ways we have not yet imagined. In the vast, echoing silence of this cosmic hollow, the universe challenges us to confront the limits of our knowledge. It invites us to acknowledge that we do not yet understand the full spectrum of forces that shape reality. It reminds us that emptiness can be as rich with meaning as fullness, that darkness can reveal truths that light cannot illuminate, and that the universe, in all its immensity, still holds mysteries far deeper than we have dared to expect. The universe often reveals its deepest mysteries, not through the brilliance of its stars, but through the haunting vastness of its darkness. And among all the chasms that punctuate the cosmic landscape, none evokes more awe and unease than the largest void ever detected. This enormous gulf of near-perfect emptiness is not merely a missing puzzle piece. It is a revelation that the puzzle itself might be larger, stranger, and more intricate than we ever imagined. To gaze into its depths is to experience a kind of cosmic vertigo, a sensation that something essential slipped through the fingers of creation long before galaxies and stars began their luminous dance. It is an artifact from an era long forgotten, imprinted into the structure of the cosmos like a scar, a reminder that even the universe bears the memory of forces more ancient than the galaxies themselves. What makes this void even more unsettling is the stark contrast it creates with the cosmic web that surrounds it. Everywhere else, the large-scale structure of the universe assembles into an intricate network, a vast architecture of filaments, nodes, and galaxy clusters woven together by dark matter and gravity. This network forms the backbone of the cosmos, guiding the movement of matter like the branching arteries of a living organism. Yet this void stands apart as a rupture in that cosmic anatomy. The filaments that should lace through this region vanish, leaving behind a desert so immense that even the most optimistic simulations struggle to recreate it. When cosmologists attempt to model the universe's evolution, the void appears as an outlier so extreme that it might as well defy probability itself. Its presence suggests that something foundational about our understanding of cosmic structure is incomplete. Dark matter lies at the heart of this puzzle. This mysterious substance, invisible yet dominant in its gravitational influence, forms the invisible skeleton of the universe. Without it, galaxies would not form, stars would not cluster, and the cosmic web would collapse into a formless haze. Yet in this vast void, dark matter seems to have evaporated or been forced outward. The density of dark matter is far below what the standard cosmological model predicts, a deficiency so severe that it has driven theorists to re-examine the assumed properties of dark matter itself. Perhaps dark matter behaves differently under extreme conditions. Perhaps it interacts with unknown fields or particles that become active only in regions of profound emptiness. Or perhaps what we perceive as a void is not simply a region devoid of matter, but a region where the laws governing dark matter diverge subtly from the norms that operate elsewhere. The void's gravitational footprint extends far beyond its physical boundaries. Galaxies that skirt its edges show signs of deformation, their shapes stretched subtly by tidal forces. Large-scale surveys reveal clusters drifting toward the void's periphery, not due to attraction, but due to the lack of competing gravitational pull within the void. This creates an unusual gravitational gradient, a slope in space-time that funnels matter around the void, like wind circulating around a pressure system. In this sense, the void shapes the behavior of its environment much like a celestial weather system, influencing cosmic flows across distances that stretch into the hundreds of millions of light-years. These flows reveal a pattern. Matter streams around the void in coherent currents, converging into dense regions where galaxy formation is enhanced, creating walls and superclusters that appear as though they have been emboldened by the void's retreat. The existence of these dense walls only heightens the mystery. They are among the most concentrated regions of galaxies ever observed, forming structures that seem too pronounced to have arisen purely from gravitational collapse. The sharp transition between the void and these dense regions violates the smoothness one would expect from standard gravitational evolution. Instead of a gradual gradient, there is a sudden drop in density, a cosmic cliff where normal structure ends abruptly and emptiness begins. This abruptness hints at a process far more dynamic than simple gravitational smoothing, a process that could involve exotic physics or early universe phenomena that amplified density contrasts in ways we do not yet understand. The void also raises questions about the very nature of spacetime. General relativity describes how matter curves spacetime to create gravity, but what happens when spacetime lacks matter on unimaginable scales? Within the void, spacetime seems to behave as though under tension, stretching and expanding more vigorously than in denser regions. This behavior could indicate that dark energy, the mysterious force accelerating the expansion of the universe, may not be uniform after all. If dark energy is stronger in regions of underdensity, it would have profound implications for the fate of the cosmos. It would mean the universe is not expanding like a balloon inflating uniformly, but like a vast landscape where valleys of emptiness deepen faster than the surrounding plains. The void could represent an early example of how space itself fractures into regions with differing expansion rates, a trend that might define the universe's far future. The faint galaxies trapped within the void stand as melancholic symbols of cosmic survival. Their isolation is so extreme that their nearest neighbors may lie tens of millions of light years away, a distance so vast that any gravitational or material interaction is nearly impossible. These galaxies age in seclusion, deprived of the triggers that ignite star formation and stimulate growth. Their stars are ancient, their gas reserves minimal, and their structures fragile. They represent evolutionary dead ends, cosmic hermits drifting through a realm that seems tailor-made to extinguish them. Their very existence suggests that the void has not always been so empty. These galaxies may be remnants of a time before the void reached its full extent, artifacts from a primordial era when filaments crossed the region but later evaporated as the void expanded. Their alignment along a faint linear structure supports this theory, a ghostly filament that persists like the last heartbeat of a dying organism. This ancient filament may hold critical clues. Its persistence implies that some underlying structure still exists, a delicate trace of dark matter that resisted the void's expansion or was left behind during a more violent process. If the void formed rapidly, perhaps through an exotic early universe mechanism, this filament could be the fossilized remnant of an earlier cosmic landscape. Alternatively, if the void developed gradually, the filament may represent the final stage of structural collapse, an indication of how the cosmic web unravels under extreme conditions. In either scenario, the filament invites comparison to relics left behind after catastrophic geological events on Earth, structures that reveal not the event itself, but the shape of the world before it changed. The void complicates our understanding of cosmic evolution. Standard cosmological models rely on the assumption that, on large enough scales, the universe becomes homogeneous. This assumption underpins everything from galaxy distribution models to predictions about the ultimate fate of the cosmos. But the existence of a void so large and so empty challenges this assumption. It suggests that the universe may harbor regions that deviate dramatically from statistical norms, regions where evolution proceeded differently. If one such void exists, others may as well, hidden across the cosmic expanse, waiting for high-resolution surveys to expose them. The cosmic web may be less uniform than imagined, shaped by forces operating at scales that exceed our current understanding. The void's connection to inflation, the rapid expansion that occurred fractions of a second after the Big Bang, presents one of the most intriguing avenues of exploration. Inflation predicts that quantum fluctuations in the early universe were stretched to astronomical scales. These fluctuations became the seeds for galaxies and clusters. But what if some fluctuations were unusually large, or were amplified by interactions between fields we do not yet understand? Such anomalies could create regions of extreme density, both overdense and underdense. The void could be a direct descendant of such a fluctuation. If so, it contains encoded within its dark expanse the memory of quantum processes that shaped the infant universe. Studying it is akin to reading the fossil record of creation itself, deciphering the language of the cosmos at its most fundamental scale. Even more speculative possibilities arise when considering ideas from string theory and multiverse hypotheses. Some models propose that our universe contains multiple vacuum states, regions where fundamental forces operate with slightly different strengths or where the vacuum energy differs. If inflation created bubbles of differing vacuum states, boundaries between these bubbles could yield radically different cosmic structures. The void might be one such boundary. Its emptiness would reflect not the absence of matter, but the incompatibility of matter with the vacuum state inside the region. Matter could never condense there because the rules governing its behavior would subtly differ. Such a concept, though bold, would provide a coherent explanation for the void's scale, shape, and behavior, unifying its anomalies under a single elegant framework. But even without invoking exotic physics, the void remains a profound reminder of the cosmos's complexity. It teaches that the universe is not merely a uniform expanse punctuated by galaxies, but a dynamic tapestry shaped by competing forces: gravity, dark matter, dark energy, quantum fluctuations, and perhaps other influences yet unknown. It reveals that emptiness is not simple. Emptiness has structure, history, and consequences. It exerts influence. It evolves. It shapes the cosmos as powerfully as the brightest clusters and largest superclusters. And perhaps most importantly, the void underscores how much we have yet to understand. In its depths, we confront our own limitations, our models, our assumptions, our desire for neat and predictable explanations. The void challenges all of these. It stands as a silent testament to the universe's unruliness, its refusal to be fully mapped or fully known. It whispers that reality is stranger than our equations allow, that the cosmos still holds secrets vast enough to humble even the most advanced scientific instruments, and that the greatest mysteries often reside not in what we see, but in what is missing. The deeper astronomers peer into the colossal gulf carved into the universe's vast architecture, the more they realize that the void operates like a kind of cosmic mirror, reflecting not light, but the limitations of human understanding. Its immensity strips away the familiar anchors that guide our comprehension of cosmic evolution, leaving behind a haunting landscape where the rules that govern everything else seem to blur. In this strange domain, forces behave differently. Matter moves according to unseen constraints, and space-time stretches in ways that diverge from the conventional rhythm of cosmic expansion. To explore this abyss is to confront the possibility that the universe contains hidden dimensions of behavior, degrees of freedom that become visible only where matter is nearly absent. It is an unsettling reminder that the cosmos expresses its complexity not only in the abundance of its luminous structures, but also in the silence of its emptiness. The void's interior is a realm defined by the absence of matter, but paradoxically, it is rich with invisible processes. Subtle gravitational gradients weave through its volume like faint tides, guiding the sparse galaxies that wander too close. These gradients create zones of accelerated expansion, where space itself stretches more aggressively than in neighboring regions. Some cosmologists interpret this as evidence for spatial variations in dark energy density, suggesting that the vacuum energy driving cosmic acceleration might not be uniform after all. If dark energy behaves like a dynamic field, rather than a constant, the void becomes a natural laboratory for observing its most extreme manifestations. In this sense, the void may not merely be a passive region where matter is scarce, but an active participant in reshaping the cosmic landscape, amplifying its own emptiness through a feedback loop of expansion and retreat that echoes through billions of years. The effect of this expansion becomes evident when observing the behavior of galaxies that skirt the void's boundary. These galaxies move not simply in response to gravitational attraction from neighboring clusters, but also in response to the void's repulsive gravitational signature, which pushes them outward along trajectories that defy the expectations of standard cosmological models. Peculiar velocities, often exceeding hundreds of kilometers per second beyond the predictions of cosmic expansion alone, testify to the void's gravitational influence. These motions trace elegant arcs and sweeping currents across intergalactic space, forming patterns that resemble atmospheric flows on a planetary scale. Just as wind converges around regions of low pressure, galaxies and dark matter stream around the void's edges, creating immense river-like structures that persist over cosmic timescales. These flows, once mapped, reveal a dynamic portrait of the void as a central engine in a sprawling gravitational system. It is within these gravitational rivers that astronomers find some of the most compelling signatures of the void's power. The galaxies caught in these currents often exhibit signs of environmental stress, their outskirts stripped by the thin intergalactic medium that sweeps past them. Star formation becomes inhibited in some systems, while others show bursts of activity triggered by gravitational compression as they drift through denser regions. These transformations underscore the void's role not merely as an empty space, but as a sculptor of galactic evolution. Over billions of years, the void's growth has influenced the histories of countless galaxies across a region spanning far beyond its visible boundaries. Through its gravitational shadow, it imprints its presence onto regions of space that appear, at a glance, unaffected by its emptiness. The void's morphology offers another clue to its origins. Rather than appearing as a perfect sphere, the void reveals a complex, irregular shape with elongated boundaries and subtle internal gradients. These irregularities suggest that the void did not arise from a single primordial fluctuation, but instead evolved through the merger of several smaller empty regions that gradually coalesced. This process resembles the merging of soap bubbles in fluid. Individual voids drift together, forming tenuous bridges before collapsing into a unified cavity. Traces of these ancestral subvoids remain as faint density variations within the larger structure, each one carrying remnants of different cosmic epochs. It is likely that some subvoids formed earlier than others, and their fusion into a single massive void preserved their chronological layering like geological strata. The galaxies that inhabit these interior layers reflect this diversity, displaying variations in their chemical compositions, ages, and distributions that align with models of multi-stage void assembly. This merging process also offers insight into the void's accelerating expansion. When smaller voids combine, the gravitational potentials that govern them overlap and intensify, generating a stronger overall repulsive effect. The new, larger void expands faster than any of its progenitors, magnifying the underdensity and pushing surrounding structures outward with greater force. Such a phenomenon could explain why the void today appears to expand faster than the cosmic average. It may represent not an anomaly, but the natural endpoint of hierarchical void evolution, a process driven by cosmic expansion, modulated by dark energy, and shaped by the initial distribution of matter in the early universe. If void mergers are indeed common, then the universe's large-scale structure may be far more dynamic than previously assumed, with vast empty regions continually shifting, joining, and reshaping the cosmic web. The void's emptiness also casts a profound influence on the propagation of light. Photons that travel through the void encounter fewer gravitational perturbations, meaning their paths deviate less than those traversing denser regions. Yet paradoxically, the void causes these photons to emerge cooler and more red-shifted than expected, a consequence of gravitational effects associated with evolving underdensities. This phenomenon subtly alters the cosmic microwave background, CMB signal, imprinting a cold signature across the patch of sky where the void resides. The size and shape of this cold imprint provide a unique window into the void's internal structure and expansion history. Through these temperature variations, astronomers can reconstruct how the void changed over billions of years, inferring its original density, its growth rate, and the role of dark energy in shaping its evolution. CMB signatures thus become fossils of the void's earliest stages, preserved not in the galaxies that managed to survive within it, but in the ancient radiation that blankets the universe. If the void indeed reflects primordial fluctuations amplified by inflation, then it may serve as direct evidence for the physics that governed the universe when it was less than a trillionth of a second old. Inflation stretched quantum-scale irregularities to cosmic proportions, seeding both the densest galaxy clusters and the emptiest voids. Examining a void of this size allows cosmologists to test inflationary models with unprecedented precision. Different versions of inflation predict varying distributions of density fluctuations. Some produce smooth, nearly Gaussian fluctuations, while others allow for more dramatic deviations. The existence of an exceptionally large void could favor models in which inflation produced rare but extreme underdensities, challenging more conservative interpretations of early universe physics. If the void aligns with predictions from models of enhanced fluctuation variance, it could provide the first large-scale observational evidence supporting these more exotic versions of inflation. The void's potential connection to exotic matter or modified gravity adds another layer of intrigue. Some theoretical models propose the existence of fields or particles that interact weakly with both normal matter and dark matter, but exert influence over cosmic expansion. These hypothetical fields could accumulate in underdense regions, amplifying the void's expansion rate and altering the behavior of matter that passes through it. If such fields exist, the void may represent a concentration point where their effects become measurable. Observations of galaxy velocities, gravitational lensing patterns, and CMB distortions may soon allow researchers to test these theories. If confirmed, the void would not merely be a cosmological oddity, but a beacon pointing toward new physics, an arena where the unknown reveals itself not through what exists, but through what is conspicuously missing. But even without invoking new physics, the void's existence forces a re-evaluation of long-standing assumptions about cosmic homogeneity. For decades, cosmology has relied on the principle that the universe becomes statistically uniform on the largest scales. This assumption underpins models of cosmic expansion, galaxy formation, and matter distribution. Yet the void's sheer size and emptiness challenge this notion, suggesting that large-scale inhomogeneities may be more significant than predicted. If the universe contains multiple voids of comparable magnitude, its expansion history may differ subtly from current models. The clustering of galaxies, the distribution of dark matter, and even the interpretation of supernova data could be influenced by the presence of vast empty regions that distort gravitational fields across cosmic distances. Understanding these effects will be essential not only for refining cosmology, but also for interpreting future observations from next-generation telescopes. The psychological impact of the void is harder to quantify, but equally profound. It confronts humanity with a vision of cosmic isolation more extreme than any previously imagined. While galaxies and clusters evoke a sense of connection and structure, the void embodies the opposite, a sweeping expanse where the universe's creative forces appear to have fallen silent. Its lonely galaxies drift through an ocean of darkness so complete that they might as well be the only islands in an otherwise lightless cosmos. For civilizations that might arise within such isolated galaxies, the universe would appear desolate, devoid of structure, and fundamentally incomprehensible. Their night sky would hold none of the clues that led humanity to discover cosmic expansion, dark matter, or the existence of other galaxies. Their science would evolve in a vacuum, not just physically, but epistemologically, shaped by a worldview in which the cosmos appears immeasurably small. Yet from another perspective, the void represents one of nature's most powerful teachers. Its existence reminds us that the universe is not governed solely by the familiar interplay of matter and gravity. It reveals that emptiness is as influential as substance, that voids shape the cosmos as profoundly as clusters, and that the absence of matter can reveal truths that remain hidden in regions overflowing with stars. The void stands as a frontier of knowledge, a region where the universe strips itself down to essentials, exposing the bare framework upon which everything else is built. In studying it, astronomers are not merely cataloguing an oddity, they are tracing the deep currents that shape the universe's evolution, uncovering the laws that preside over vast scales, and glimpsing the profound simplicity that lies beneath the cosmic web's complexity. The void remains an unfolding enigma, its origins uncertain, its physics incomplete, its implications vast. Each new observation deepens the mystery, revealing threads that lead into realms of theory not yet fully formed. It reminds us that even after centuries of astronomical exploration, the universe still holds domains that resist understanding, places where our most confident models tremble at the threshold of the unknown. And in that resistance lies the promise of discovery. For the void is not merely empty space, it is a cosmic invitation to expand the boundaries of human knowledge. The search for answers within the largest void in the universe has pushed observational astronomy to the threshold of its technological capabilities. Every new instrument aimed at this immense gulf reveals that emptiness is far more complex than anyone anticipated. What first appeared to be a simple absence of matter has transformed into a profoundly layered mystery, filled with subtle structures, anomalous dynamics, and faint signatures of forces that slip between the cracks of classical cosmology. As the void yields its secrets, it becomes increasingly clear that its existence is not merely a statistical outlier, but a challenge to the very framework used to interpret the cosmos. The deeper one studies this region, the more striking its contradictions become, as though the void itself were a deliberate puzzle embedded within the cosmic tapestry, a riddle written in the language of absence. The void's discovery created an immediate tension between observation and theory, a tension that persists today. According to the standard model of cosmology, density fluctuations in the early universe should have produced a relatively well-behaved distribution of voids, numerous small ones, fewer mid-sized ones, and an extremely small number of giant voids that fall off rapidly in probability. Yet the largest void defies even the most generous expectations. Its volume is so enormous that its probability of forming under standard assumptions borders on the impossible, suggesting that the void emerged through processes that current models do not account for. Some researchers propose that the void may have been seeded by an unusually deep primordial underdensity, while others argue that environmental factors might have amplified an initially small fluctuation. Yet neither explanation fully resolves the observed discrepancies, leaving the void suspended at the boundary between the explicable and the extraordinary. The internal architecture of the void complicates the picture even further. Instead of a uniformly empty region, astronomers have identified delicate strands of ultra-faint matter connecting small galaxy groups, like thin threads stretching across a chasm. These barely detectable structures resemble the remnants of dark matter filaments that once shaped the region, but have since decayed or evaporated through gravitational evolution. Their fragility suggests that the void has been expanding and deepening for billions of years, steadily eroding the cosmic scaffolding that might have once supported more robust galaxy formation. These ghost-like filaments, detectable only through their weak gravitational imprints or faint diffuse emissions, represent some of the last vestiges of structure within a region that has nearly surrendered to the relentless pull of emptiness. Among the void's most intriguing inhabitants are the ultra-faint dwarf galaxies scattered sporadically throughout its interior. Each one represents a defiant spark of cosmic resilience, glowing weakly against the overwhelming backdrop of darkness. These galaxies are astonishingly fragile, collections of stars so sparse that the distance between neighbors may stretch across vast fractions of a light year. Their low star formation rates, minimal gas reserves, and unusual chemical compositions point toward a history shaped by severe environmental deprivation. Lacking nearby galaxies to interact with, these dwarfs evolve in near-perfect isolation, unperturbed by tidal forces or mergers that typically drive galactic evolution. Their existence raises questions about the minimum conditions required for galaxy formation and the thresholds below which normal processes fail. That such galaxies survive at all speaks to the resilience of cosmic structure, persisting even in environments seemingly hostile to its emergence. The behavior of dark matter within the void has become one of its most fascinating and troubling mysteries. Standard cosmology predicts that dark matter should permeate the void, though at a lower density than in galaxy-rich regions. Yet gravitational lensing measurements indicate that the void contains far less dark matter than expected, with some analyses suggesting a deficit so large that it challenges the assumed universality of dark matter distribution. Several hypotheses have been proposed to explain this anomaly. One possibility is that dark matter may interact with itself or with other fields in underdense environments, causing it to diffuse outward more rapidly than standard models predict. Another proposal suggests that exotic forms of dark matter, such as warm or self-annihilating varieties, might behave differently in regions where gravitational confinement is minimal. If any of these theories prove correct, the void could become a crucial proving ground for understanding dark matter's true nature, offering insights that cannot be obtained from galaxy-rich regions where gravitational forces dominate. The void's gravitational influence extends well beyond its physical boundaries, shaping the motion of matter across distances approaching 1 billion light-years. This influence appears in the peculiar velocities of galaxy groups that skirt the void's edges, many of which exhibit motion patterns that deviate significantly from cosmological predictions. These velocities chart elegant arcs around the void, suggesting the presence of a massive gravitational basin that redirects cosmic flows, much like a river bends around a canyon. Observations reveal that matter near the void moves preferentially toward denser regions, creating a striking contrast between convergent flows outside the void and divergent flows within it. Such patterns reveal the void's role as a dynamic engine within the cosmic web, one that exerts influence not through presence, but through absence. The void creates a vast gravitational vacuum, a region where matter naturally drains away, reshaping the flow of cosmic structures over billions of years. As astronomical instruments grow more sensitive, researchers have begun detecting subtle forms of matter within the void that were previously invisible. Observations in the infrared and radio wavelengths have revealed patches of warm dust drifting through the void, faintly glowing against the cold background of space. These dust structures form tenuous bridges between dwarf galaxies, suggesting that some form of interaction or shared origin links them despite their vast separation. More puzzling still are the diffuse radio emissions detected in certain regions of the void. These emissions do not correspond to known galactic processes and may indicate the presence of exotic plasma structures or interactions between cosmic rays and extremely low-density gas. Although these signals are faint, their very existence demonstrates that the void is not a perfect vacuum. Instead, it contains traces of matter and energy that may represent the last echoes of processes that once shaped this now silent region. Some of the most tantalizing signatures emerging from the void come from the search for gravitational waves. Theorists predict that exotic objects such as primordial black holes, cosmic strings, or domain walls might appear more readily in underdense regions where interactions with normal matter are minimal. If such objects exist, they may generate faint gravitational wave signals that travel unobstructed through the void, offering a rare opportunity to detect relics from the earliest phases of the universe. Future space-based detectors may be able to pinpoint anomalies in gravitational wave propagation that correspond to the void's internal geometry or composition. By analyzing how these waves stretch, compress, or redirect as they pass through the region, scientists could map the void's structure in exquisite detail, revealing features hidden from electromagnetic observations. The void also plays a crucial role in refining cosmological models. The distribution of large voids across the universe reflects the pattern of density fluctuations produced during inflation, the rapid expansion that occurred fractions of a second after the Big Bang. By studying the size, shape, and frequency of voids, cosmologists can test competing inflationary theories and constrain parameters that describe the early universe. The largest void, in particular, challenges the notion that inflation generated fluctuations of uniform variance. Instead, it suggests the possibility of either enhanced fluctuations or localized events, such as phase transitions or variations in the inflaton field, that produced unusually deep underdensities. If the void represents the imprint of such an event, it could serve as direct evidence for inflationary models that incorporate non-Gaussianity, multi-field interactions, or early universe symmetry breaking. In this way, the void becomes a bridge between observational cosmology and high-energy physics, linking the structure of the present-day universe to the quantum landscape that preceded it. Among the most imaginative, but not implausible, interpretations of the void is the idea that it may represent a boundary between regions of the universe with differing vacuum states. Some theoretical frameworks, including those inspired by string theory, propose that the universe may contain multiple vacuum configurations, each defined by different fundamental constants or particle properties. If inflation generated a patchwork of such regions, the boundaries between them could appear as enormous voids where matter fails to condense due to incompatible physical laws. In this view, the void is not merely empty space, but a portal of sorts, a region where the fabric of reality differs subtly from that of the surrounding universe. While such ideas remain speculative, they offer a striking explanation for the void's extreme properties, unifying its anomalous expansion, unusual gravitational behavior, and scarcity of dark matter within a single elegant framework. Despite its overwhelming darkness, the void is not an endpoint, but a beginning. It represents a frontier in the truest sense, a region where nature's rules reveal unexpected depth. The largest void demonstrates that emptiness is not simple, nor is it uniform. It is dynamic, structured, and profoundly influential. It carves channels through which matter flows, shapes the evolution of galaxies, alters the behavior of light, and offers a canvas upon which new physics may one day be written. The void challenges humanity to confront the cosmos, not as a static backdrop, but as a living, evolving entity marked by tensions and contrasts as striking as those between stars and darkness. As observations improve and theories sharpen, the void will continue to act as both test and teacher. It demands answers to questions that cut to the core of modern cosmology. What governs the distribution of matter on the largest scales? Why does dark matter behave differently in this region? Is dark energy uniform, or does it vary with cosmic environment? What relics from the early universe might lie hidden in this immense chasm? The void refuses to be dismissed as an anomaly. Its presence shapes the universe more deeply than many luminous structures ever will. It forces us to reconsider the foundations upon which our understanding of the cosmos rests. And in doing so, it brings us one step closer to the humbling truth that despite centuries of discovery, the universe remains vast, untamed, and filled with wonders that exceed the boundaries of imagination. Across the vast cosmic landscape, the largest void stands as a reminder that even the universe's silence can be deafening. It is a region where the usual signposts of cosmic evolution seem to vanish, leaving behind a realm shaped more by what is absent than by what remains. Each new observation reveals a deeper layer of contradiction within this unimaginable expanse, suggesting that the void is not simply an anomaly, but a doorway into a chapter of cosmic history that was never fully written in the galaxies we know so well. The profound stillness inside this region conceals an undercurrent of dynamism, hinting that emptiness itself may be an active force sculpting the evolution of the cosmos. And as researchers analyze the faintest whispers of matter within the void, they find hints that even this silence hides a complex and ancient story, one that intertwines gravitational physics, dark energy, quantum processes, and the faintest echoes of the early universe. The void presents a gravitational paradox that has intrigued and unsettled cosmologists in equal measure. Its underdensity is so extreme that traditional gravitational models struggle to explain how it could have grown as large as it is in the available cosmic time. In normal structure formation, voids deepen as matter flows outward into surrounding filaments and clusters. Yet in this vast chasm, the process appears amplified, far beyond predictions. This intensification implies that some mechanism, gravitational or otherwise, accelerated the evacuation of matter from this region. Such a mechanism could be cosmological in nature, linked to properties of dark energy or early universe inflation, or it could arise from more exotic physics, such as interactions between dark matter and hypothetical scalar fields. In either scenario, the void becomes a laboratory for testing how matter responds to forces that may have been at work since the universe's earliest instance. One of the most striking features of the void is the clarity with which it divides the cosmic web. The universe, when viewed on sufficiently large scales, resembles a vast interconnected network with filaments of dark matter and gas-bridging galaxy clusters across millions of light years. But here, in the presence of the largest void, the web seems unnaturally torn. Filaments that should extend smoothly across space terminate abruptly at the void's boundary, as though something suppressed their formation within this expanse. This abrupt cessation challenges the principle that the cosmic web forms uniformly wherever dark matter collapses. Instead, it suggests that the void may have prevented dark matter from condensing in the first place, or disrupted an earlier stage of filament development. If this interpretation holds, the void represents a structural defect in the cosmic web, a region where the universe's most fundamental organizing principles failed to operate as usual. This structural disruption is reflected in the arrangement of the few galaxies that inhabit the void. Rather than being scattered randomly, they appear aligned along faint linear paths, barely surviving relics of what may have been embryonic filaments. Their distribution is so peculiar that it has prompted speculation about the void's earlier stages. Perhaps the region once contained a nascent cosmic structure that never reached full maturity, arrested in its development by a sudden shift in density or expansion rate. Or perhaps these galaxies formed independently of the cosmic web, their gravity allowing them to remain intact even as the surrounding environment dissolved into emptiness. Their faintness, their low metallicity, and their slow evolution all point toward lives shaped in profound isolation. These galaxies are like cosmic fossils, preserving conditions that may have vanished elsewhere billions of years ago. The void's impact extends far beyond its borders, influencing the flow of matter around it. Observational surveys reveal that galaxy clusters near the void exhibit unusually high degrees of anisotropy in their motions, moving preferentially away from the void as though responding to a repulsive force. While general relativity predicts that underdensities create effective gravitational wells that push matter outward, the magnitude of this effect in the largest void exceeds theoretical expectations. This discrepancy has fueled speculation that dark energy may behave differently inside such regions, intensifying the local rate of expansion. If dark energy is not constant but varies with matter density, then voids could represent pockets where its influence becomes magnified. In this interpretation, the void is not only empty, but actively expanding at a rate slightly greater than the cosmic average, stretching space-time like a membrane under tension. This creates a cascading effect in which emptiness accelerates its own growth, potentially offering clues about how dark energy might shape the universe's distant future. Along the void's periphery, some of the densest structures known to astronomy appear. These colossal walls, containing thousands of galaxies packed together across hundreds of millions of light-years, form a dramatic counterpoint to the void's emptiness. Their existence implies that matter displaced from the void accumulated at its boundaries, much like debris gathering around the shores of a retreating tide. The sharp gradient between the void and these dense walls suggests that the void's formation may have been more abrupt than gradual, perhaps triggered by an early universe event that rapidly evacuated matter from its center. Alternatively, the walls may have formed through a process of gravitational competition, where filaments bordering the void grew stronger by drawing in matter that would otherwise have formed structures within the void. These walls act like cosmic fortresses, standing guard around a territory where normal structure formation faltered. The void's relationship with the cosmic microwave background, CMB, provides one of the most compelling clues about its ancient origins. The CMB reveals a subtle cold patch where photons lose energy while traversing the void, an effect attributable to evolving gravitational potentials. This imprint, known as the integrated Sachs-Wolf effect, implies that the void has been growing more empty and more dynamically active over billions of years. Yet the magnitude of the cold spot does not fully align with predictions, suggesting that either the void is more complex internally than previously thought, or additional physical effects contribute to the observed signal. Some studies propose that the void may contain slight temperature variations in its sparse gas or faint, undetected structures that interact with passing photons in unexpected ways. Others suggest that time-evolving vacuum energy within the void affects photon travel more strongly than anticipated. Either explanation points to physics that is not yet fully captured by standard cosmological models. The question of whether the void contains exotic matter remains open, though accumulating hints suggest the possibility. Observations of faint X-ray emissions in patches of the void imply that hot gas is present in quantities too small to detect through traditional surveys. This gas could represent the remnants of early structure formation, heated by shocks as matter fell toward the void's outer walls. More intriguingly, some theoretical models propose that voids may harbor concentrations of hypothetical particles, such as axion-like fields or ultralight scalar fields, that exert subtle gravitational effects without interacting strongly with normal matter. If such particles accumulate preferentially in underdense regions, they could influence the evolution of voids in measurable ways, altering expansion rates, gravitational potentials, and even the propagation of light. Detecting such effects would revolutionize our understanding of dark matter and the quantum fields that may permeate spacetime. The void also presents a unique opportunity for studying cosmic neutrinos, particles so elusive that they can pass through entire planets without interacting. In dense regions of the universe, neutrino signals are drowned out by noise from star-forming galaxies, black holes, and other energetic phenomena. But within the void, this noise is nearly non-existent. As a result, neutrinos emitted by distant cosmic events travel through the void with minimal interference, preserving information about their origins. Observatories capable of measuring these faint neutrino streams may one day map the void's interior using particle physics rather than photons, revealing structures invisible to traditional instruments. Such measurements could uncover whether the void contains relics from the early universe, frozen signatures of processes that occurred mere microseconds after the Big Bang. Beyond its scientific implications, the void offers a philosophical reminder of the universe's complexity. It challenges the human tendency to equate emptiness with insignificance. In truth, the void is one of the most influential structures in the cosmos, shaping matter and energy on scales that dwarf entire superclusters. Its presence forces a reconsideration of long-held assumptions about cosmic evolution, matter distribution, and the physics governing the early universe. It demonstrates that absence can be as powerful as presence, and that the universe's deepest mysteries often lie not within blazing galaxies, but within the quiet expanses where creation paused. As technological advances push astronomers closer to mapping the void with unprecedented fidelity, the region stands poised to become a cornerstone in the next era of cosmological research. Future observatories will probe its faintest structures, its gravitational subtleties, and the behavior of fundamental particles as they traverse its depths. They will test models of inflation, dark energy, dark matter, and modified gravity against the void's anomalies, using its unusual properties as touchstones for evaluating competing theories. In this way, the void serves as both a challenge and a guide, a region where the universe expresses its most enigmatic behaviors, urging discovery through its silent expanse. Ultimately, the void compels humanity to recognize that the cosmos is not governed by uniformity, but by a balance between structure and emptiness, between creation and dissolution, between the luminous and the unseen. In studying this vast emptiness, we encounter the possibility that the universe is shaped as much by its voids as by its galaxies, that the forces sculpting the cosmos extend beyond the reach of familiar physics, and that the deepest truths may reside not in what the universe contains, but in what it deliberately leaves blank. The void stands as a monument to the profound mysteries that define existence, a cosmic enigma inviting us to peer into its depths, not with fear, but with curiosity, humility, and the unwavering desire to understand. The deepest truth of the universe may not lie in the brilliance of stars or the violence of black holes, but in the profound silence of cosmic emptiness. And nowhere is that silence more eloquent than within the largest void ever discovered, a colossal realm where the absence of matter speaks louder than its presence. This vast region, stretching across hundreds of millions of light years, stands as one of the most perplexing structures known to science. Its existence challenges the foundations of cosmology, forcing a reconsideration of how structure forms, how the early universe behaved, and what hidden forces may still shape the cosmos today. As researchers continue to probe its depths, they find that each discovery within this void uncovers more questions than answers. It is as though the universe carved out this immense emptiness not as a flaw, but as a message, an invitation to study what happens when nature steps back and leaves a canvas almost entirely blank. The void's narrative begins in the earliest instance after the Big Bang, long before galaxies formed, or light could travel freely through space. During the epoch of inflation, the universe expanded exponentially, stretching quantum fluctuations into macroscopic structures. These primordial fluctuations seeded the density variations that eventually became galaxy clusters, filaments, and voids. But the largest void stands apart as an outlier, a region where the initial density was not merely lower than average, but drastically so. This suggests that something unusual occurred during inflation, perhaps a fluctuation of rare magnitude, or the influence of an unknown field that subtly altered the behavior of space itself. If this interpretation is correct, the void is more than an astronomical curiosity. It is a relic of inflation, a direct imprint of physics that operated on energy scales far beyond anything achievable in laboratories. Studying it is akin to observing the faint trace of a cosmic event so ancient that it predates the formation of even the simplest atoms. As the universe evolved, gravity amplified these primordial fluctuations, drawing matter into denser regions while underdense zones became emptier. In typical voids, this process eventually slows as matter redistribution approaches equilibrium, but in the largest void, the process appears to have accelerated instead. Its boundaries show signs of rapid expansion and intensified gravitational evacuation, suggesting that the void's growth has been influenced by forces beyond gravity alone. Observations indicate that space inside the void expands slightly faster than the cosmic average, implying that dark energy may behave differently there. If dark energy becomes stronger in regions of low matter density, then voids could act as amplifiers of cosmic expansion, growing faster as they become emptier. This possibility aligns with models of quintessence, where dark energy is not a constant, but a dynamic field that evolves over time and varies across space. In this framework, the void becomes a laboratory for understanding how the universe's most mysterious component, responsible for its accelerated expansion, interacts with the cosmic landscape. The influence of this accelerated expansion is evident in the galaxies that reside near the void's edges. Their velocities reveal a pronounced outward drift, as though they are being gently pushed away from the void's interior. This outward motion exceeds what would be expected from cosmic expansion alone, suggesting that the void exerts a repulsive gravitational effect. While gravity itself cannot create repulsion, the behavior is consistent with how dark energy influences space-time. In a region where dark energy density is higher than average, space expands more rapidly, effectively pushing matter outward. If the void contains such a concentration, it would represent one of the clearest natural experiments ever observed for studying dark energy in isolation. Its emptiness becomes its defining feature, not merely the absence of matter, but the presence of a force that shapes the fate of the cosmos. The void's gravitational influence extends not only to nearby galaxies, but also to the cosmic web at large. Filaments surrounding the void show signs of distortion, bending around the vast emptiness as they channel matter along gravitational pathways. These distortions form elegant arcs that trace the invisible contours of dark matter. Yet within the void itself, dark matter seems to be startlingly scarce. This challenges the assumption that dark matter permeates all regions of the universe uniformly. Instead, it suggests that dark matter may have been evacuated from the void or never accumulated there to begin with. Some theories propose that dark matter experiences subtle interactions that become significant only in extremely low-density environments, causing it to diffuse outward. Others suggest that the void may contain a variant of dark matter, with properties that differ from the standard cold dark matter model. If correct, the void could be the first direct evidence for dark matter diversity, a hint that the dark sector contains multiple components, each governed by its own rules. Yet perhaps the most enigmatic feature of the void lies in the galaxies that inhabit its interior. These faint, isolated systems defy conventional expectations for galactic evolution. They are small, dim, and chemically primitive, with low star formation rates and minimal interaction history. Without nearby galaxies to merge with or gravitational tides to reshape them, these galaxies evolve in slow motion, aging quietly over billions of years. Their isolation offers a unique window into what galaxies might have looked like in the early universe, before the cosmic web matured and environmental effects became dominant. Some of these galaxies contain stars so old that they approach the age of the universe itself, suggesting that their formation was among the earliest episodes of star creation. Their ancient stellar populations provide clues about conditions in the first few 100 million years after the Big Bang, conditions that have been erased in most other galaxies through mergers, accretion, and internal evolution. The distribution of these galaxies within the void is even more peculiar. Rather than forming a random scatter, They align along faint, thread-like structures that resemble degraded filaments. These structures stretch across tens of millions of light years and may represent the remnants of an embryonic cosmic web that never fully developed. If so, the void could preserve the initial mapping of dark matter seeds before the web matured. In most regions of the universe, these seeds blossomed into intricate filaments that guided galaxy formation. But here, in this region of extreme underdensity, the process may have stalled prematurely. The galaxies that remain are therefore not merely isolated survivors. They are markers of a cosmic history that diverged from the norm. Their alignment reveals the fingerprints of structure formation in an environment that never reached maturity, a glimpse into an alternate pathway of cosmic evolution. The void's connection to the cosmic microwave background, CMB, adds yet another layer to its mystery. The cold patch observed in the CMB toward the void's direction suggests that photons lose energy while traversing its interior, a signature consistent with evolving gravitational potentials. But the magnitude of the cold spot is not fully accounted for by the void alone. This discrepancy has led to speculation that the void may be associated with additional physical processes, perhaps residual heat from early universe phase transitions, or interactions between photons and exotic particles in the void's near-vacuum environment. Another possibility is that the void coincides with a region where inflation operated differently, producing subtle imprints in the CMB that persist to this day. If true, the void may serve as a boundary marker between regions of space with slightly different inflationary histories. The possibility that the void represents a remnant of a domain wall, a boundary between regions of the universe with different vacuum states, has captivated theorists. In some models, inflation does not produce a perfectly uniform universe, but instead generates a mosaic of domains, each with its own vacuum energy or fundamental constants. Most such domains would be separated by walls that collapse or dissipate quickly, but a rare surviving boundary could produce a region where matter fails to form normally. If the void corresponds to such a primordial domain wall, it would offer unprecedented insight into physics beyond the standard model, including the shape of the energy landscape that governed inflation. In this scenario, the void is not merely a lack of matter, but a relic of an earlier cosmic phase, a window into physics that shaped the universe long before galaxies emerged. Technological advances promise to transform our understanding of this mysterious region. Next-generation telescopes will map the void in unparalleled detail, detecting ultra-faint galaxies, measuring dark matter distribution with higher precision, and tracing the motion of cosmic flows with greater accuracy. Space-based observatories will analyze subtle distortions in the cosmic microwave background caused by the void's gravitational effects. Neutrino detectors may one day capture streams of particles passing through the void, revealing whether it contains exotic matter or hidden interactions. Meanwhile, gravitational wave observatories could detect anomalies in wave propagation caused by the void's unusual space-time geometry. Each of these tools brings humanity closer to decoding the void's secrets, peeling back the layers of silence to reveal the physics that shaped it. Ultimately, the void stands as one of the universe's greatest paradoxes. It is vast, yet nearly empty. It is silent, yet filled with clues about cosmic evolution. It is dark, yet illuminated by the faintest echoes of ancient processes. In its emptiness lies a story of creation, expansion, isolation, and the delicate balance between presence and absence that defines the structure of the cosmos. The void forces us to confront the possibility that the universe is not uniform at its largest scales, that laws we assume to be universal may vary with environment, and that the early universe contained complexities still hidden in the cosmic backdrop. In studying this immense emptiness, humanity gains not only scientific insight, but philosophical perspective. The void reminds us that the universe does not owe us simplicity. It does not promise clarity. Instead, it offers mystery, a reminder that discovery thrives at the boundaries of the known. The void is one such boundary, a cosmic threshold where current theories falter and imagination begins. It calls to us not through light, but through silence, urging us to listen closely to what emptiness reveals about existence itself. Thank you for watching. If you enjoyed this video, leave a like and share your thoughts in the comments. Send it to someone who you think would enjoy this topic too. And of course, subscribe and turn on the notification bell so you don't miss the next videos. See you next time.